All right. Well, thanks for having me here in Medellin. It's my first time in Colombia, so I will have a slow start to the talk to allow people to arrive. I know it's early on a Saturday morning. So in this talk, I'm going to speak a little bit about my entire career up until now. So I got involved in Python in 2008, and so many of you know I started working on pandas in my first job, and it was not an open source project. So the first year and a half or so, it was purely built to use inside AQR, where I was working, and we released the project at the end of 2009. And it became an open source project, but it didn't really become popular or develop a community until a couple of years later. I've worked at a number of different companies who've been really great in supporting my work. I started a company in the middle called DataPad, and the thing that may surprise many people is that since sometime in 2013, I haven't been involved in day-to-day pandas maintenance and development since 2013, which is almost 7 years ago, which surprises a lot of people. And so I'm sure to tell people about that, which also gives me an opportunity to talk about the amazing community that Pandas has built. In the last 4 or 5 years, I've been working on the Apache Arrow project, which I see as a continuation of the work that I started in Pandas, and I will tell you a bit more about that later in the talk. Okay, so I've been involved in the community for 12 years. A lot has changed. So first, I would like to point out that Pandas just had, after 10 years, its 1.0 release, which is the 26th major release of Pandas. The project has had around 2,000 unique contributors over its lifetime. The project now has a new logo, which was contributed by Indeed.com. So thank you very much to Indeed, and thank you to Mark Garcia for working with Indeed on the logo. But if you go back in time, the very first release of Pandas came out in December 2009, which is still on PyPI, so you can download it and look at it, and you'll find that it's a much smaller code base that doesn't do very much. Pandas just received its first formal funding, its first formal grant in 2019 from the Chan Zuckerberg Initiative, which has been set up to give money to open source projects. Until that point, most of the developers have, in particular the core developers who are doing maintenance on the project, have been volunteers and have been funding their time either out of their nights and weekends, and in some cases, and in particular, Anaconda has been a really great supporter of Pandas, and we now have, I think, one and a half or two developers from the Pandas core team are employees of Anaconda, and so to have, it's very important to have people whose job it is to maintain an open source project, and for it to not be their night and weekend project. So I worked with a few people in the early days of Pandas just for historical interest. I worked with Chang Shi and Adam Klein at AQR, and I recruited them to work with me on Pandas in 2011, 2012 era. And so if you look back at the commit logs, you'll see that Chang and Adam did a bunch of critical work in the project, and I certainly wouldn't have been able to get the project to where it is today without their help. Since then, Pandas has built a really amazing core developer team, and has anyone contributed a patch to Pandas, like a pull request? Okay, we got a couple pull requests, but so we've built the project has built a really amazing and active developer team. So many, if you go on the project, you may interact with Jay Reback. That's Jeff Reback. He's a real person. He's not a bot. It seems like it sometimes because you file an issue and he responds in 2 minutes. So Mark Garcia, some of you have interacted with because he has really done a lot of community organizing and community development. And I will say about Mark and people like Mark is that there are many ways to have a big impact on an open source project beyond writing code, and some people don't think about that. And so organizing meetups or organizing code sprints or working with companies to get sponsorship or getting companies to contribute to a project are very valuable. And sometimes people are only looking at the Git log and saying like, okay, well the Git log is the only thing that matters, but there's big ways to contribute to a project beyond Git commits. So the core developer team has started meeting up in person the last few years. We met up, so some of us in 2019, we met up in Nashville, and I think that the core team intends for that to be an annual ritual. Some of you may have seen at the beginning of 2018, Pandas had a documentation sprint, a worldwide documentation sprint, which was organized by Mark Garcia, and I think yielded, I don't know how many pull requests, but like over 100 pull requests to improve Pandas's documentation. And this is the kind of thing that I think we need to see more of in open source projects, basically outreach efforts to bring in new contributors and to work on some of the less loved parts of projects, like the documentation. So a lot of people were complaining about Pandas's documentation. Pandas is a really big project, so we had a worldwide documentation sprint to improve it. So taking a bit of a step back from Pandas, I'd like to talk about Python's journey to becoming a mainstream data language. And it's interesting because to many people, particularly business people, so maybe not you, but maybe your boss and your boss's boss, it seems like Python got really popular for working with data all of a sudden. It kind of did in a way, but the story is a lot more complex than that. And so I'd like to talk about my personal experience being involved in that process. So in 2011, at SciPy, I wrote a paper about pandas. This was about 3 years into the project. And I said that we believe in the coming years there will be great opportunity to attract users in need of statistical analysis tools to Python who might otherwise be using another programming language. Pandas provides a foundation upon which a very powerful data analysis ecosystem can be established. Now, in 2011, this was still very much hopes and dreams. It wasn't the reality. We still had a lot of work to do in order to make this possible. So, since that point, Python, relative to other programming languages, many of you may have seen this analysis from Stack Overflow in 2017. That Python as a programming language went from around 3 or 4% market share as far as Stack Overflow questions, which is not exactly representative of reality, but it's a rough proxy. So Python has become a great deal more popular. And so when Guido van Rossum was retiring last year, some people were looking at this data and said, how did Python got so big? Why did it start growing so much around this time frame? And Guido said, well, did it all at once? To me, it has felt like 29 years of exponential growth. And I hate to disagree with Guido in a talk, but the story is more complex. So if you dig into the Stack Overflow data, you see that many of Python's core use cases that existed around 2010, namely web development. So if you went to PyCon in 2010, so my very first PyCon was 2010, you would not hear much about, the term data science didn't exist in 2010. You would not hear much about data analysis or statistics or machine learning. PyCon in 2010 was really about web development and building the backends of web applications. And so if you look at the data, the overall interest in web development frameworks has increased along with the general interest in Python, but it's really the scientific applications and the data analysis applications that you know, at least according to the data, have led a lot of the growth in use of Python. And so you can see that in the data. And so nowadays, I think that more than if you control for, I guess, high-income countries and some other data cleaning, you know, I think around 1% of questions on Stack Overflow are about pandas. Of course, many people say, well, the problem is that pandas is really confusing, and so people are asking a lot of questions about it. That may also be true. So what I said to Guido on Twitter back in August was that my view was that it was around the 2011, 2012 timeframe that Python began to be accepted in professional circles as a language to use for data analysis. And so that means basically that your boss was okay with it. And to get to that point where your boss would say it's okay for this team to use Python was a lot of work and was not a sure thing, at all. And so what I said was that in that time frame, Python was still considered an untrusted and a risky programming language, and so many companies with sensitive applications, so think like financial firms, insurance companies, companies with a lot of money, they would stick with really safe things that seemed safe. Like nobody wanted to take technology risks and risk losing their job, and so at that time it felt like Python was a risk. And in my first job, that was an uphill battle that I faced, getting Python to be accepted as a primary programming language to use. So there's a number of factors that I believe have driven Python's growth during this period. So one big thing is the overall, huge need for people to work with data. So not only people to do machine learning and people to do AI, but also people to do data cleaning and more mundane data work. So a lot more data is being collected, a lot more data is coming in the door. We need people to be able to write SQL queries and write data munging scripts as quickly as possible to clean up the data and ingest it into a form where it can be managed and analyzed. So all of those data wranglers and data scientists wouldn't be able to use Python unless we had the necessary tools. And so around this time, there was a coalescing, kind of a coming together of what I call a perfect storm of packages. I will talk about those. Another dimension, which you'll hear more from tomorrow from Fernando, is that there was a big push in universities to set up cross-disciplinary data science education, because everyone heard about data science, and let's say you're 18 years old, and in the past maybe you would say, I want to study computer science. Now everyone's showing up and saying, I want to learn data science. What's that? So universities set up programs to teach data science, and having the programming language in use be as accessible as possible and could be learned as quickly as possible was very important in making these programs successful. So the fact that Python, quote unquote, gets out of your way, I think that's Fernando's tagline for Python, that university programs could teach Python in a few weeks to their students and then move on to the actual real work of working with data and doing data analysis. So those things were not enough. There also needed to be some successful early adopters, and so I think around this time, like 2011, 2012, there were enough companies that had begun using Python and they started reporting that the world had not blown up, and that things were going okay for them. And so that was also very helpful in getting kind of to have the peer validation, so that when your boss would call somebody else's boss at another company and say, hey, all of my employees want to use Python, is that cool? Should I let them do that? And around this time, they started to say, yeah, it's okay. And the last thing is packaging improvements. So if you can't install the software consistently on all of the platforms that you're using, the whole ecosystem is dead in the water. So this is not a complete listing of some of the perfect storm of packages, but certainly it was absolutely necessary that we had the computational foundation to build on. So without NumPy and SciPy, scikit-learn would never have existed, pandas would never have existed. Without Jupyter, we wouldn't have had an accessible, interactive environment to do exploratory computing and develop and share work. Without Matplotlib, for all of its, for all of the love and hate that we throw at it, we wouldn't have been able to visualize data in many different contexts. I often cite Cython as being one of these perfect storm packages because it made writing C extensions a lot more accessible to Python programmers. And so, one of the mantras in Python is being able to do all of your high-level work in Python and then find your computational bottlenecks and speed up those selectively with C code or C++ code. So, so often people say to me that they think that pandas was a major catalyst for the growth of the ecosystem, and I think it definitely helped for a variety of reasons. But it's one of those things where the whole is greater than the sum of its parts, and we really needed all of these things for the whole thing to work. So kind of stepping back a little bit in time, I want to talk a little bit about the kinds of problems that I faced trying to socialize Python in 2008. So when we talk, we often say about these things, we call them fear, uncertainty, and doubt. So I also had the problem that I was 23 years old in 2008, so I had age working against me. So you can imagine somebody who had just graduated from the university saying, hey, let's use a new programming language with a bunch of packages built mostly by graduate students, and let's you do that instead of Java. And it didn't go over that well. So some of the common concerns that I faced, which sometimes people don't think about. So one thing is issues that arise in very large code bases. And so people would say to me, yes, we see that you as an individual are very productive writing Python, and you can sit down and you can write a ton of Python programs and solve a bunch of problems. But what happens when there are 100 people working together on a Python code base? What do million-line Python code bases look like? And that speaks kind of to the kind of long-term life cycle of software, and there become a lot of problems that arise in these very large code bases around how do we do refactoring, how do we manage deprecations and issues, so code that was written by somebody who may no longer work at the company, and maybe he or she did not write any unit tests, and now it's kind of this stinking pile of code that has to be maintained. And it was felt, at least at that time, that Java, which was the preferred language in 2008, that the language afforded enough obviousness when things were broken. So when something was broken, it was very obvious in Java, by the nature of the compiler. And IDEs in Java provide a lot of machine-assisted refactoring, and so that provides, people were very comfortable with extremely large code bases in Java, and they had not developed that level of comfort with Python. There were, of course, the problems and the kind of, I wouldn't say they're misconceptions, but people's preconceptions about interpreted languages. They would say interpreted languages are unsafe because we don't have types, we don't have a compiler, and interpreted languages are slow. And the answer to that is interpreted languages can be unsafe and interpreted languages can be slow. But with Python, you have to, particularly in teams, it's very important to institute software development practices that mitigate some of these risks. And so the importance of, and so I would cite that many Java developers would write code and say, okay, Java C works, it compiles, so it's done. And so there would be many applications that wouldn't have sufficient unit tests because the compiler was giving this false sense of security. And so part of addressing this fear, uncertainty, and doubt is re-educating people about software development practices, and that using an interpreted language to build big software requires a different approach. The last item, which is an ongoing issue even now in 2020, is getting people to be comfortable building on top of open source. And that one's difficult, because then you end up looking at a project, like who builds this project, what dependencies does this project have, who builds those projects, and so people aren't really sure where the bugs are going to be coming from and where the risks are. And so, I think it's another thing where it means that you have to be defensive about writing tests to ensure that when you upgrade a package, when you upgrade NumPy, when you upgrade pandas, that your code still works the same way that it did a year ago. So, in May 2011, and I think you may hear from Fernando a little bit about these meetings that we had. We recognized in 2011 that we had there was a lot of opportunity to expand the use of Python, but we had work to do. And so my argument to the group, and there were about a dozen or 15 of us in the room in Austin, Texas, kind of a strategic core developer meeting, was that we need to make sure that we have a robust set of tools that can be used in production. It's also good for interactive research and is accessible to less sophisticated programmers. And we have to fix packaging. So, no small tasks. I had some other concerns around the time that we had kind of this loose federation of open source projects, but there wasn't a great deal of cross-project coordination. And so I'd been working on pandas for about 3 years, but there was at that point there was little integration of pandas with other projects. So if you would wrangle data in pandas, the next step you would do would be to export the data to NumPy and then use another project. So there wasn't, no one was using pandas as a dependency at that time, and I felt that the community needed to work to have more stronger dependencies on each other to create a more holistic and kind of cohesive end-to-end experience of working with data. And it took time for this to happen, and it's understandable that when projects are new and they're developing that, it's difficult to trust and depend on other open source projects because everyone has their own motivations and their own incentives. Another thing to keep in mind in 2011 is that it was still difficult to read CSV files in Python. And many people take this for granted now because you open up Jupyter and you write pandas read CSV, but that wasn't always the case. And so I think in these kinds of discussions, it's very important to ground the discussion in what some of these practical problems. Like, let's make sure we can read a CSV file, do a little bit of data cleaning, and make a plot. So if we can do that consistently in 99% of cases, then we've made a lot of progress. And so I often tell people that I think that one of the reasons that pandas became popular is because of pandas read CSV. And I don't think that's too much of a stretch. So anyway, I guess some of you know the rest of the story. I guess things worked out. You know, people started adopting Python. There were a lot of other things that happened. You know, I felt that educating people in these tools was very important. So I wrote my book in 2012, and I think that helped a lot of businesses and universities feel more comfortable about adopting Python, because they could hand a book to people and say, read this book, and then you will be able to work with data. And so this was a long time ago now. It was almost 8 years ago that I was writing the book. I did a second edition in 2017. I don't think that there is a Spanish edition, which is unfortunate, and many programming books are not translated into Spanish, which also makes me sad. I've talked with the book publishers, and book publishers are book publishers. So I know that with some books, like, I don't know if anyone knows the book R for Data Science. There's a community effort to create an open source translation of R for Data Science into Spanish. So those kinds of things happen, but I hope that the book publishers will do more to serve the Spanish-speaking community in the future. So a little bit into what I've been doing with my life for the last 6 or 7 years. After 5 years of working on pandas, I started to experience some discontent with some of the problems, particularly computational problems that I had to solve in the course of building pandas. And this was driven in part by, starting around this time frame, let's say 2013, I was trying to use pandas, and many other people were using pandas essentially as a substitute for a SQL database or a system that does analytical queries. And we started to run into a number of performance and memory use problems, which I memorialized in this talk, which I called 10 Things I Hate About Pandas. And around that same time, I started working at Cloudera, and I found that there was a Java-based data analysis ecosystem which had been working for 6 or 8 years without thinking about Python at all. So you had tons of money being spent, tons of developers designing file formats, building data processing engines, distributed computing systems, and Python was a total afterthought. And so there were a number of problems there. So there were a lot of file formats that Python could not read. Interacting with the JVM, in particular moving data and large data sets in and out of the JVM, was very difficult and very expensive. And a lot of the interfaces for working with data in Java and these systems that had been built, like Hadoop, were not array-oriented, and Python is very much about array-oriented and vector-based computing. And so my job when I got to Cloudera was, we want you to do something about the Python big data problem. So I kind of had these two experiences. We had built a ton of code in pandas for processing data. We still had a lot of performance problems, and then we see, okay, Python is not yet a big data citizen. And we knew about some of the problems, so not to go too much into the technical details, but some of these problems exist in R as well. But working with very large data sets, so data sets that are at the limit of what you can fit into your computer's RAM, or maybe bigger than RAM, very difficult to work with. The data types supported by pandas and by R are pretty limited, and so in the big data world, you have much larger type systems for describing data. So you would have arrays and structures and unions and things that couldn't be represented in NumPy. Some of the performance problems in pandas came from strings. And this is also a problem in R. And so there's currently some work in pandas to improve string memory use and performance, but it's of course coming, a very long time into the project. So it's been, if it's happening 10 years into the project, you can bet that it's a difficult problem to solve. And so one of the issues with pandas is that it's kind of this Swiss Army knife, and it's notoriously big in terms of the number of functions that it has. And I'm sure many of you have been pounding the table and shaking your fist at the documentation for pandas read CSV. Say, why does pandas read CSV have 50 options? And it's because real world data is messy, but pandas deliberately optimized for wanting to be that Swiss Army knife with all of these tools and all of this flexibility to handle a huge amount of different use cases. And in particular, to have a lot of versatility and a lot of fine-tune control over complicated data sets. Those were mostly focused on smaller data sets that fit into memory and where memory use was not really a concern. And so when you're working with very large data sets, we're talking like terabyte or 100 gigabytes, you don't need all of these tools, and the set of operations that you need in general to work with those data sets is a smaller kind of set of ideas. So, you can imagine the feedback you might get on a Swiss Army knife, like 1 star does not cut down trees. In reality, the feedback that we get is like, well, I ran out of memory with 10 gigabytes of CSVs. So a lot of people have been discontented about this, and there was a moment in 2013, 2014 where what people were beginning to say was, well, there's this new thing called Apache Spark, and maybe all of this code that you all have been writing for Python, it's just going to be replaced by Spark, and you're going to be in the future using a programming API on top of Spark, and so maybe you should stop writing all of this computing code and just, build integrations with Spark. Well, obviously this didn't really happen. So I think one of the big things that sort of changed the equation was the appearance of Tensorflow and basically current generation AI and machine learning frameworks. So we have the creators of Spacey here, so a lot of people are using Spacey. So to suddenly have Google release TensorFlow in 2015, and then everyone in the world says, okay, we need to use this, we need to use TensorFlow, we need to do AI. What is the programming language of AI? It's Python. So there was this massive tectonic shift that happened in 2015 where everyone said, okay, well, maybe we need to invest a lot more in Python. So on my end, what I've been doing to address some of the issues that I've encountered is thinking about the kind of the infrastructure and systems level of how we work with data and how we build and reuse code to process that data. And the primary, and so from my experience in pandas, my feeling was that pandas took on responsibility for solving too many problems. So there's a ton of custom code and a ton of custom algorithms. There's a lot of data ingest, and pandas is a very large project with like hundreds of thousands of lines of code at this point. And wouldn't it be great if we could own less of this code and there was more computational foundations for analytics that could be reused for working with DataFrames? The problem, of course, is that everyone's data frame is a little bit different, and so the code that is written that processes a pandas data frame cannot be taken and reused in R, and so that's an issue. So what we did, a big group of open source developers, we said we need to design basically a new memory representation for data frames that is not specific to Python or any programming language. And we want it to be something that can be adopted widely by all programming languages and can be a general computational foundation for analytics. And for me personally, I wanted to see kind of a marriage between the data science community, the database ecosystem, people building SQL databases, and the Java big data ecosystem. No small task. So kind of the big picture of going from this world where we end up having to copy and serialize data inefficiently between a million different n-choose-2 combinations to a common data frame representation which can be reused at the data level and at the code that can be reused for computation across runtimes and programming languages. So I've been working on this for the last 4 or 5 years. I think it'll be 5 years, middle of this year. So the project is growing. It's obviously an ambitious and very big project and involves a lot of programming languages as well. So that increases the complexity of building something like this. So we now have some level of support for 11 programming languages, and the community is growing pretty rapidly. Kind of our big picture is that we want a memory layout that is very efficient to process on modern hardware. We want to be able to memory map and access very big data sets without having to load all of the data into RAM, and for that memory mapping to be not a language-specific feature. And so the fact that you can interact with binary data in JavaScript without serializing, without converting it, or in Java or in C++ or in Python is very useful, and it's very nice to have all of that working. And another big deal is that we want 2 different runtimes that are running inside the same process in your computer to be able to access each other's data without any conversion. So it's been difficult to achieve this, but yeah, this is what we've been working on. So on the C++ and Python R side, not to go too much in detail with this, we're building a core data processing platform that has some pieces attached to it, so some computational building blocks, which we're calling query engine, part of the system. We're building a datasets framework which deals with accessing, reading, and writing different file formats. Some other stuff we're working on, like we build a messaging framework, so if you're sending big data sets over TCP on a network, we have a system called Flight for that, but you can go online and read about all of this if you're interested in all of the gory details. But the big thing about Arrow, and what many people often ask me about is, Wes, do I need to care about this? Do I need to install this? And ideally, as an end user, as a data scientist, you shouldn't have to interact much directly with this. The audience for Apache Arrow is the developers of other open source projects and people building databases and data processing systems. I would be remiss to not mention that currently there is a new crop of what I will call new DataFrame projects happening in Python. Some of these you may have heard of, some that I may have missed. These are very exciting, and I think these are projects which started up to address the performance and scalability issues with pandas. Some of them use pandas directly, like DataFrame and Modin use pandas directly. NVIDIA's Rapids project and VAX do not use pandas directly as a computational building block. Rapids is based on Arrow and is entirely GPU based. So, but there's 40, 50 people at NVIDIA working on it, so it's a big project for them. So I think it's really great to have these new projects innovating on performance and scalability for Python programmers. What I would like to see kind of in the long run in these projects is to have more collaboration and more code reuse at the fundamental computation level. So unification at the data representation level, so namely kind of what we're doing with Arrow, and having code that is reused, code to perform, group by operations and aggregations and so forth, that is high quality and can be used, reused interchangeably in these projects. I will also say, since I only have I've got 4 minutes left, there's some really good things that we can learn from the R community. Maybe maybe that's heretical to say here at a Python conference. I work for RStudio now, it's funny that I work for an R company, true story. But the R programming language has some very cool things in it. So one thing is that the idea of building a domain-specific language, you write code, and that code is manipulated and translated by other code that you write into the thing that you actually want to do. And it has enabled our programmers to mold the language to have very expressive code for describing data analysis and data manipulation. And some of this we can't really do very easily in Python because of the nature of how Python executes code. So when you write R code, every piece of R code that you write is, it's evaluated at the very last moment. And so what you can actually do is when you call a function, the arguments to that function aren't evaluated yet, and you can inspect them and you can manipulate them. So it enables expert developers to rewrite the code that you were writing into the thing that you actually intended. And so that leads to very concise and very rich code for doing data manipulation. It is possible to do some of this stuff in Python, but it requires a more explicit and approach to building deferred, lazy APIs that create unevaluated objects. So rather than you write A plus B, you get an object that is add A to B, and then it's not evaluated until you actually ask for it to be evaluated. So just to show you kind of things that we're working on for our programmers, this is dplyr code that takes a data set, groups by some fields, selects some fields, aggregates, and filters. And so what we're working toward for our programmers is to be able to take this code completely unevaluated and to optimize the operations, to simplify and combine them to be as efficient as possible, and then to execute this analysis in a parallel runtime. Obviously, we'll expose the same functionality in Python, but it's interesting that R already has the API that is lazy and does not know anything about Arrow and can be integrated very naturally, whereas we have to do more work in Python to either retrofit projects like pandas with new computational functionality or develop new APIs for lazy evaluation of analytics. So I will close with one last item, which is that it is very difficult to fund and support ambitious new open source projects. I haven't figured it out personally. So last year, you may have seen a little bit about this. I partnered with RStudio to found Ursa Labs, which is a nonprofit organization that works on the Apache Arrow project. So we were funded by RStudio and a collection of other sponsors, which at the moment are mostly hardware companies like NVIDIA and Intel and financial firms. And so these are all companies that have strategic interest in the open source work that we were doing. We aren't building any products or selling anything, so it's not a startup. We're purely just doing open source development. I think this is a pretty good model because it helps get strategic alignment from corporations which have a lot of resources, aka money and people, and who want to use the project to solve business problems that they have. So this is working well for us. I don't know that it will work well for every open source project, but there's many different ways to fund open source, and so this was for me partially an experiment to find a more scalable model to do nonprofit open source development work. It also gave me a formalized way to collaborate with the R community. So the fact that we actively talk with Hadley Wickham from the R community, who's a creator of many popular R packages, creates a more of an incentive for the two programming languages to work together and to achieve shared goals. All right. So I'm done, and thank you for listening, and I look forward to meeting many of you here at the conference, and thanks again for inviting me to Medellin.